Hey kids, welcome back. Ready? Wow, 75 meters. Great job, you did it. Ooh, scholar. Okay. Um, so we saw yesterday a ball is dropped straight down. At the same exact time, another ball is launched perfectly horizontally. If you want to try this at home, it's pretty simple. You could. Is this relevant to? No, it's not relevant. I'll say it anyway. You could take like a ruler and then bend a little like index card. So bend a piece of paper like this, and or an index card, something stiff, and then stick a ruler like right there, bam, and then put a penny on each side. Then take your ruler and just kind of flick it, flick it. The penny on the front will be shot forward. The penny on the back will basically have the cards like pulled out from under it, and it'll fall straight down. You will see for only 2 cents, both pennies hit the ground at the same time. So both balls hit the ground at the same time. Yes, amazing, great. But what if it was not quite perfectly horizontally? What if, like, Mr. Sarker is amazing, obviously. Hopefully you guys told him how great he was on his video. But what if he didn't perfectly level out the launcher and it was a little bit angled up or a little bit angled down? Would they still hit the ground at the same time? Make your prediction right now. Would the ball still hit the ground at the same time? Okay. What did I say? So I said that the initial speed of the ball was 1 meter per second to the right. And it was actually to the left. Did I make a mistake on purpose? No. I mean, did I make a mistake? No, it was totally on purpose. Unlike that mistake, which was not on purpose. I made it to the right because if the launcher was not perfectly horizontal, if there was some angle theta, we can still determine the important variables. If theta is not zero, if theta is some non-zero number, some non-zero angle, this V naught will not just be Vx naught. There'll be some Vx naught and some Vy naught too. And that will affect the problem. In the problem yesterday, or last lesson, we assumed Vy naught was zero. But if theta is not zero, if there's some angle that the object is launched, Vy naught will not be zero, and that would mess up our calculations. So let's say Mr. Sarker just like totally missed, and he launched. So this is how he launched the ball. He launched it perfectly horizontal to the right. Pretend it was to the right. He launched it to the right with Vx naught equals 1 meter per second. Let me make that positive 1 meter per second. And Vy naught equals 0 meters per second. I'm gonna erase this. Even though it's a great drawing, I'm gonna erase it for no reason. What would Vx naught and Vy naught be if he launched it straight upward, directly to the left, which he actually did, or straight downward? In each of these three cases, what's Vx naught and what's Vy naught? Can you fill in this table for me? What would happen if you launched the marble upward, left, or down instead to the right? We'll use the normal coordinate axes that we normally use. Right is positive x, up is positive left. So fill out this table in your notes right now. What are Vx naught and Vy naught if the ball is shot up, left, or down? Fill out this table, please, for me right now. If it's launched upward, that's vertical, not horizontal. So Vx naught is 0 meters per second. Same with downward. Downward is vertical, not horizontal. Vx naught would be 0 meters per second. These are when the ball is launched to the right. If the ball is launched left, we'll get the reverse. Vy naught is still 0 meters per second, but instead of positive 1, we get negative 1 meter per second. If you launch it upward, you get the other thing. Positive 1, negative 1. What was the point of this whole table? Why did I waste all my time? This launcher that shoots balls 1 meter per second gives you a Vx naught and a Vy naught. But how do you find them for any angle you launch the launcher? It's a unit circle. Oh my gosh. That's why I specifically bought the exact perfect launcher that launches balls at 1 meter per second. It's a unit circle. A 1 unit radius circle centered on the origin. Whatever V, the velocity vector, initial velocity of the ball is, you can find Vx and Vy using vector resolution, which we all know that we all already know. If you know V naught and theta, you can find Vx naught and Vy naught. Vx naught is V naught cosine theta, and Vy naught is V naught sine theta. So you can do the same kind of problem you did last unit, but it's much easier. Is that what I'm saying? Yeah, it's much harder because Vy naught is not going to be 0 in this case, and Vx naught won't be 1 meter per second. It'll be probably less because of the cosine theta. I have to show you guys another fascinating simulation before we move on. So let's check it out. physics. Okay. So in this problem, let's forget the monkey. Look at the dart. Assume the dart is launched at speed v at angle theta above horizontal. You find v naught. You find vx naught and vy naught. I might have said v naught y or v naught x. It's the same thing. And basically, you take the y and the x and you plug them in into your table, just like last time. I think we're going to do some examples. It is trickier than the last problem because vy naught is 0. So a very common trick we do to make these problems easier, we assume the projectile, the thing being launched in the air, will start on the ground and land on the ground. Like if I kick a ball, like, okay, time to draw an amazing foot. Bam, that's what feet look like. If I kick a ball off the ground and it goes through the air and lands on the totally flat ground, that makes the problem much easier. Why does this make the problem much easier if it starts on the ground and lands on the ground, which is a flat horizontal plane? What makes the problem way easier if we know that? So we know Vx naught, we know Vy naught. For all these problems, Ax is 0. Ay is going to be negative 9.8 meters per second squared downward. And we just said, if you know it's horizontal flat ground, you can say dy is 0. Not always true, but often true. Should I write dy is 0 if it's true? No, that doesn't make sense. If you land at starting height, Not always the case, but a very nice shortcut if it is the case. So we're going to do a quick example problem where Vx, V naught is, let's say I launch a projectile at 35 meters per second, and let's say theta is not drawn to scale. Let's say theta is 72 degrees. So let's try this practice problem right here. And let's see how far the object goes. This is going to be a lot of calculations, this lesson. It might be a little long. Sorry about that. Okay, so let's say an object is kicked off the ground, 35 meters per second at a big angle, 72 degrees. How far does it go before it hits the ground at the same height? Another word for how far it goes if it hits the ground at the same height is the range. A really long range kick. Goes really far across the x displacement on the ground. So it's the same as yesterday's problem. We first find t. Just kidding, we first find Vx naught and Vy naught. Vx naught is V naught cosine theta. It's 10.8 meters per second. Vy naught is V naught sine theta. It's 33.3 meters per second. Now we find t. dy equals Vy naught t plus 1/2 ay t squared. Plug in 0, plug in Vy naught from here, plug in ay, negative 9.81 meter per second squared, find t. This is a quadratic function, but dy is 0. So you can do a very nice trick and divide both sides by t. So you'll actually get 0 equals vy naught plus 1/2 a yt, and then t is not quadratic, it's much easier to solve. Dividing by t actually, how do I say it, removes the solution. It removes the solution t equals 0, which makes sense because if you're finding the time when the ball is back at starting height, well, t equals 0 is a time when the ball is at its starting height. So yeah, you did it. You found it. Oh, when's the ball at its starting height? 0 seconds. But that's not the problem. That's not the problem. That's not the answer we want. We want the answer comes out to 6.8 seconds, if my notes are correct. I know I'm going really fast, so ask me in class if you want me to explain that a little more in depth. But we found time, 6.8 seconds. Then we plug that in the x side. dx equals vx naught t plus 1/2 axt squared, which I'm not going to write because ax is 0. So it's 10.8 meters per second times 6.8 seconds. This ball, or tranquilizer dart, I forgot what I said, this object will go 73.4 meters. Okay, I think I'm going to put a little more of this lesson tomorrow. So this is an example where the ball is launched off the ground and lands at the same height. dy is 0, just like yesterday. Find t, plug it in the other side. You can start the practice problems now, but you'll see a lot where they don't start and end at the same height. We'll talk about that next lesson.